Welcome to the Bedtime Lab, where we explore the wonders of the universe, one sleepy fact at a time. I'm so glad you've joined us tonight, and I hope you're feeling cozy and ready to drift into a world of fascinating knowledge. As we settle into this gentle journey, I'd love to hear where you're tuning in from. Whether you're nestled in a bustling city or surrounded by the quiet of the countryside, remember you're among friends here. Tonight, we're embarking on an exploration of nuclear fusion in stars, a topic that glows with intrigue and wonder. Let me share something interesting with you. Did you know that the process of nuclear fusion is what makes stars shine so brightly? Inside every star, including our very own sun, nuclear fusion occurs when hydrogen atoms collide and fuse together, forming helium. This process releases an incredible amount of energy, which is why stars have been shining steadily for billions of years. It's the very heartbeat of the universe. Speaking of stars, here's a fascinating fact. Our sun fuses approximately 600 million tons of hydrogen every second. Can you imagine that? Every second, the sun transforms vast amounts of hydrogen into helium, producing the light and warmth that bathes our planet. Without this constant nuclear fusion, life as we know it simply wouldn't exist. And here's something else to ponder. Nuclear fusion in stars doesn't just create helium. In the hearts of massive stars, fusion goes further, creating heavier elements like carbon, oxygen, and iron, essentially the elements that make up everything around us, from the air we breathe to the very cells in our bodies, were forged in the fiery cores of ancient stars. Isn't it incredible to think that we are, quite literally, made of stardust? Now, let me tell you about the conditions required for nuclear fusion to occur. It happens at temperatures around 15 million degrees Celsius, which is about 27 million degrees Fahrenheit. That's hotter than anything we can imagine on Earth, and is necessary to overcome the natural repulsion between atomic nuclei. The extreme heat and pressure found in the core of stars allow atoms to get close enough to fuse, releasing the energy that powers them. It's a dance of forces that takes place on a scale and intensity beyond our everyday experience. This reminds me of something truly astonishing. The light we see from distant stars has traveled vast distances to reach us, sometimes taking millions of years. So when you gaze up at the night sky, you're essentially looking back in time, witnessing the glow of stars as they were eons ago. The universe is a vast and intricate tapestry, woven with threads of light from countless stars. Speaking of the universe, here's another delightful tidbit. Not all stars produce energy in the same way. While our sun primarily fuses hydrogen into helium, more massive stars can fuse elements up to iron in their cores. When these colossal stars reach the end of their life cycles, they explode in spectacular supernovae, scattering their enriched guts across the cosmos. The remnants left behind can form neutron stars or even black holes, adding to the universe's complex and mysterious tapestry. I find it fascinating to think about the sheer scale of these processes. For instance, the energy produced by nuclear fusion in the sun is equivalent to the explosion of 92 billion 1 megaton hydrogen bombs every second. Yet, despite this overwhelming power, we only receive a tiny fraction of its energy here on Earth, just enough to sustain life and drive the weather systems that shape our planet. It's a delicate balance that sustains our world in ways we continue to discover and appreciate. And here's a little thought to carry with you. Each sunrise you witness is a reminder of the continuous nuclear fusion happening in the sun. It's a cosmic performance that unfolds with every dawn, painting the sky with colors that are both familiar and extraordinary. In its own way, every sunrise is a testament to the awe-inspiring processes that occur throughout the universe. As we continue our journey tonight, remember that the universe is full of wonders waiting to be uncovered. Each star you see in the sky is a testament to the miraculous process of nuclear fusion, a process that fuels the cosmos and in turn fuels our imaginations. The next time you find yourself under a starry sky, take a moment to breathe in the vastness of it all and appreciate the connections we share with the stars. In our next chapter, we'll delve even deeper into these celestial wonders. But for now, let your mind wander through the galaxies as you slip into a peaceful slumber. Remember, whether you're here for a brief moment or an entire night, you're always welcome at the Bedtime Lab, where the universe waits to whisper its secrets as you drift off to sleep. Let me continue with a little-known fact about our sun. It's not just a massive ball of burning gas. It's actually in a delicate balance. On one hand, there's the immense pressure from gravitational forces pulling everything inward. On the other, the energy released from nuclear fusion pushes outward. This equilibrium is what keeps the sun stable. A stellar dance that has continued for about 4.5 billion years and will continue for roughly 5 billion more. As we think about the sun's life, have you ever wondered what happens when a star runs out of fuel? When stars like our sun exhaust their hydrogen, they expand into red giants. But the story doesn't end there. Eventually, they shed their outer layers, creating beautiful structures known as planetary nebulae. What's left behind is a small, dense core called a white dwarf, a remnant that glows faintly with the last vestiges of fusion energy. You might find it fascinating that not all stars will turn into white dwarfs. In the case of more massive stars, their fate is even more dramatic. After a supernova, the core of a massive star might collapse into a neutron star. These extraordinary objects are incredibly dense, so much so that a sugar cube-sized amount of neutron star material would weigh as much as a mountain. Speaking of neutron stars, did you know they can spin at astonishing speeds? Some rotate hundreds of times per second, emitting beams of radiation that we detect as pulsars. These cosmic lighthouses are a testament to the incredible forces at play in the universe. Here's another intriguing fact. The energy produced in the core of a star doesn't reach the surface immediately. It can take thousands or even millions of years for light generated by nuclear fusion in the sun's core to make its journey to the surface and then travel to Earth. So, the sunlight that warms your face is truly ancient, a direct connection to fusion processes that occurred long before we existed. Have you ever thought about the variety of stars in the universe? Stars come in all sizes and colors, from the small and cool red dwarfs to the massive and brilliant blue giants. Interestingly, red dwarfs are the most common stars in the universe. They burn their fuel slowly and can live for trillions of years, much longer than our sun. And yet, because they're so dim, none are visible to the naked eye from Earth. Speaking of longevity, did you know that the largest stars live the shortest lives? Their massive size means they burn through their nuclear fuel at an incredible rate, sometimes in just a few million years. In contrast, smaller stars can live for billions or even trillions of years, a stark contrast to their larger cousins. Let me share a curious detail about helium, the product of fusion. It's the second most abundant element in the universe, created primarily in the cores of stars. Over time, helium accumulates, and when enough builds up, it starts to fuse into heavier elements. This marks a new phase in a star's life, leading to the creation of elements like carbon. And here's a truly cosmic thought. Every breath you take contains atoms that were once part of stars. The oxygen in our atmosphere was forged in the hearts of ancient stars, scattered into space during supernova explosions, and eventually incorporated into planets and living beings. We are, quite literally, connected to the cosmos in the most intimate way. Here's something that might surprise you. Even though stars appear constant to us, they are in a constant state of change. They pulse, flicker, and sometimes erupt in flares that send streams of particles into space. These stellar outbursts can affect nearby planets, sometimes stripping away atmospheres or bathing them in intense radiation. Thinking about the life cycles of stars leads us naturally to consider their origins. Stars are born in vast clouds of gas and dust called nebulae. Gravity pulls these clouds together, and as they contract, they heat up and eventually ignite nuclear fusion. This stellar nursery is a place of wonder where new stars emerge to light up the universe. As we ponder the vastness of space, it's humbling to consider that even the smallest stars, known as brown dwarfs, don't have enough mass to sustain hydrogen fusion like our Sun. They are often described as failed stars, yet they still shine dimly with the heat left over from their formation. And finally, let's touch on a cosmic curiosity. The universe itself began with a massive fusion event, the Big Bang, which created the lightest elements, hydrogen and helium. Every star that has ever existed is part of a continuum that stretches back to this primordial moment. It's a reminder of our place in a universe filled with ancient and ongoing processes, a never-ending cycle of creation and transformation. As these facts gently swirl in your mind, let them guide you into a deeper understanding of the universe's wonders, a vast and beautiful expanse where the light of stars tells the story of creation, change, and renewal. Stars, those distant twinkling points of light, hold within them processes so complex and awe-inspiring that they seem almost magical. One of the most surprising aspects of nuclear fusion in stars is its role as a cosmic alchemist. Did you know that every single element on the periodic table heavier than hydrogen and helium was forged in the heart of a star? This transformative journey begins with hydrogen atoms fusing to form helium, but as stars evolve, they become crucibles for creating heavier elements like carbon, oxygen, and even iron. Isn't it incredible to think that the calcium in your bones and the iron in your blood were all born from starfire? Speaking of the life and death of stars, it's fascinating to consider that the fate of a star is determined by its mass. More massive stars have the ability to fuse heavier elements in their cores. But here's the twist. Once a star begins fusing iron, it spells the beginning of the end. Fusion of iron doesn't release energy. Instead, it absorbs it, leading to a catastrophic collapse that ends in a supernova. This explosive end not only scatters the elements into space, but also triggers the formation of new stars and planets. The universe is quite the recycler, wouldn't you agree? Let me share something remarkable about the conditions required for fusion. Temperatures in a star's core must reach millions of degrees to overcome the natural repulsion between atomic nuclei. For our Sun, this means core temperatures soar to around 15 million degrees Celsius. The pressure is equally overwhelming, with the weight of the outer layers bearing down on the core, compressing it to densities unimaginable on Earth. This extreme environment is both a furnace and a crucible, where hydrogen nuclei collide and bond, transforming into helium through a process known as the proton-proton chain. Here's a captivating idea. The energy produced in a star's core is not just heat and light. Fusion generates neutrinos, ghostly particles that zip through the universe at nearly the speed of light, barely interacting with matter. Right now, billions of neutrinos are passing through your body every second, a silent reminder of the sun's ceaseless activity. Talking about nuclear fusion naturally brings us to the concept of the Chandrasekhar limit, a critical threshold for white dwarfs. If a white dwarf exceeds about 1.4 times the mass of the Sun, it can no longer support itself against gravitational collapse. This limit is crucial because it determines whether a star will end its life as a quiet white dwarf or in a dramatic supernova explosion. Another aspect that might catch you by surprise is how stars of different masses follow distinct fusion pathways. Smaller stars, like our Sun, primarily utilize the proton-proton chain reaction. However, more massive stars have enough temperature and pressure to engage in the carbon-nitrogen-oxygen cycle, a more complex fusion process that produces energy at a faster rate. This difference in fusion mechanisms is a beautiful example of how nature tailors processes to fit every star's unique characteristics. And if you're intrigued by vast numbers, consider this. In the Milky Way galaxy alone, it's estimated that a star is born every few seconds. Each new star signifies a new opportunity for fusion to begin its alchemical work, transforming elements and lighting up the universe. Here's a thought-provoking fact. Heavy elements created in stars are distributed through galaxies by supernovae and stellar winds, enriching interstellar space. This process of cosmic seeding means that new stars are born with an initial supply of heavier elements, contributing to the diversity of planets and ultimately life itself. Let me tell you about a curious phenomenon related to fusion in massive stars. As they age, these stars develop layered structures like onions, with each layer fusing a different element. It's a complex, multi-layered process that ultimately leads to the synthesis of iron at the core. This stratification is a testament to the dynamic and intricate nature of stellar evolution. Did you ever wonder how scientists study the processes happening inside stars when they're so far away? They use a technique called helioseismology, which involves studying the oscillations on a star's surface to infer details about its interior. It's akin to listening to musical notes to understand the instrument creating them, a beautiful blend of art and science. There's a poetic symmetry to how stars begin and end with fusion. Massive stars that explode as supernovae provide the shock waves necessary to trigger the collapse of nearby gas clouds, leading to the birth of new stars. Thus, the death of one star sows the seeds of another, ensuring the cycle of stellar life continues unabated. Lastly, consider this amazing fact. While nuclear fusion is a common process in stars, it remains a challenging endeavor to replicate here on Earth. Scientists are working tirelessly to develop fusion power as a sustainable energy source, hoping to harness the same processes that power the stars to provide clean energy for our planet. So as you drift off to sleep, picture the stars above and all the extraordinary processes taking place within them. Each one is an active participant in the grand narrative of the universe, a reminder of the brilliant mechanisms that turn the wheels of cosmic time, weaving the fabric of existence with threads of light and elements forged in stellar fires. Let me share a rather enchanting thought. Within the heart of every star, a delicate balance exists between gravity pulling inward and fusion pushing outward. This equilibrium is vital for the star's stability. When the balance tips, either due to exhaustion of fuel or changes in fusion rates, the star's life enters a new phase, often leading to dramatic transformations. Can you imagine how sensitive these cosmic giants are to the forces at play within them? Speaking of transformations, consider the fascinating role of magnetic fields. These invisible forces can significantly influence fusion processes in stars. In some cases, strong magnetic fields can redirect the flow of plasma, affecting where and how fusion occurs. It's as if stars have their own internal compass, guiding the brilliant reactions that light up the cosmos. Here's something intriguing. Stars in binary systems, where two stars orbit a common center of mass, can engage in a form of cosmic dance that influences their fusion activity. These interactions can lead to mass transfer or even the merger of the stars, resulting in intensified fusion and spectacular outbursts known as novae. The gravitational embrace of these stellar partners showcases another layer of complexity in the fusion narrative. Did you know that the Sun, often considered the quintessential star, is actually quite average in the vast context of the universe? Despite being our primary source of light and energy, it is merely one of billions of stars, each engaging in fusion with its own unique characteristics. This average nature allows the Sun to sustain a steady output over billions of years, providing a stable environment for life on Earth. Let's delve into the mysteries of red giants. These stars, in the later stages of their evolution, expand to enormous sizes as they burn through the last of their hydrogen fuel. During this phase, the core contracts and heats up, enabling helium fusion into heavier elements. The outer layers swell, often engulfing nearby planets. Imagine the immensity of such a star, its fusion-driven heart maintaining a precarious balance as it contemplates the next stage of its journey. Here's a captivating thought. Not all fusion processes are equal. In some of the universe's most extreme environments, such as in the immediate aftermath of a supernova, neutron capture processes occur, rapidly converting lighter elements into heavier ones. This phenomenon, known as the R process, is responsible for creating many of the heaviest elements in the universe. It's an extraordinary testament to the transformative power of fusion under extreme conditions. If we turn our gaze to blue supergiants, these massive stars are known for their short but brilliant lives. Their immense mass allows them to burn through their nuclear fuel at a staggering rate, undergoing multiple fusion stages in rapid succession. As they near the end of their life cycle, they often explode as some of the most luminous supernovae, enriching the cosmos with the elements forged in their fiery hearts. Consider this. While supernovae are dramatic and explosive, some stars end their lives in a more subdued manner. Low to intermediate mass stars, like our Sun, will eventually shed their outer layers, leaving behind a hot core called a white dwarf. This remnant continues to glow from leftover heat, despite fusion having ceased. It's a quiet, yet poignant reminder of a star's enduring presence, even after its fusion days are over. The story of fusion wouldn't be complete without mentioning variable stars. These stars exhibit changes in brightness due to pulsations within their outer layers. Such pulsations can alter the internal conditions, affecting fusion rates. Imagine a star breathing in and out, its glow fluctuating as it navigates the complexities of its internal dynamics. Let me paint a picture of stellar nurseries, those vast clouds of gas and dust where stars are born. Within these regions, gravity pulls material together, increasing temperature and pressure until fusion ignites. These birthplaces of stars are teeming with the raw potential for fusion, waiting for the right conditions to spark a new generation of celestial objects. Here's a thought-provoking detail. The lifespan of a star is intricately linked to its mass and therefore its fusion activity. Massive stars burn through their fuel quickly, living fast and dying young, while smaller stars can sustain fusion processes for billions, even trillions of years. This disparity in lifespans highlights the diverse pathways that fusion can take depending on a star's initial conditions. It's quite extraordinary to think that, despite the violent and chaotic nature of the universe, fusion within stars provides a constant source of light and energy. This stability allows for the emergence of complex systems, like our solar system, capable of supporting life. The predictability of fusion reactions, despite the immense scales and energies involved, is a cornerstone of cosmic order. Lastly, ponder this: stars aren't just inert sources of light, but active, evolving entities. As they undergo fusion, they emit winds of charged particles, influencing their surroundings and contributing to the dynamic nature of galaxies. These stellar winds, driven by fusion, act as a gentle yet profound force, shaping the universe in subtle and beautiful ways. And so, as you close your eyes, let these tales of nuclear fusion in stars fill your thoughts. Each fact we've explored weaves a little more understanding into the grand tapestry of the universe. May the wonders of the stars bring you peace and curiosity as you drift into the realm of dreams. Imagine for a moment how the stars we see twinkling in the night sky are like cosmic time capsules, each one a storyteller of nuclear fusion. This process, which powers the stars, is not only a brilliant dance of atoms, but also a complex saga that unfolds over eons. Have you ever wondered how stars of different sizes and compositions affect fusion? It's fascinating to note that the temperature and pressure at a star's core dictate the type of fusion that occurs. For instance, small stars primarily fuse hydrogen into helium, while larger stars proceed to fuse helium into carbon and oxygen, and so on down the line of heavier elements. This sequence is like a cosmic alchemy, transforming the simple into the complex. Speaking of transformations, red dwarfs present an intriguing case. These small, cool stars burn their fuel so slowly that they can last for trillions of years, far longer than the current age of the universe. In their leisurely pace, red dwarfs provide a stark contrast to the hurried life cycle of massive stars. Did you know that in some red dwarfs, fusion can become so efficient that there's almost no waste? This incredible efficiency means that these stars will burn nearly all of their hydrogen before moving on to the next phase of their life cycle. Let me share something about carbon stars. These are stars that have an abundance of carbon in their outer layers, resulting from unique fusion processes. The carbon, combined with other elements, creates molecules like carbon monoxide, giving these stars their distinctive reddish appearance. It's a vivid reminder of how fusion within a star can directly influence its color and appearance. And here's a curious phenomenon. The process of fusion in stars is so powerful that it creates neutrinos, nearly massless particles that can pass through almost anything, even the entire Earth. Neutrinos produced by the Sun's fusion reach our planet in vast numbers every second, yet they rarely interact with matter. Imagine these particles as silent messengers carrying information from the core of the Sun to us, undisturbed by their journey across the cosmos. Consider this surprising fact. In very massive stars, fusion can proceed all the way to iron. But here's the twist. Fusing iron doesn't release energy. It actually requires energy. Once a star begins to accumulate iron, it marks the end of its ability to produce energy through fusion. This buildup of iron eventually leads to a catastrophic collapse, triggering a supernova explosion. Such an event is both an end and a beginning, scattering elements throughout the universe that may one day form new stars, planets, and even life. Speaking of new life, did you know that the fusion processes in stars are responsible for creating almost all the elements in the universe? Everything we see, from the calcium in our bones to the gold in our jewelry, owes its existence to the crucible of stars. It's as if we carry within us the remnants of ancient stars, a poetic connection to the cosmos. Let's turn our attention to a fascinating concept. Fusion in stars is not only an energy source, but also a stabilizing force. A star's gravity constantly tries to collapse it, but fusion generates outward pressure that counters this collapse. This balance, known as hydrostatic equilibrium, is what keeps stars stable over long periods. Imagine the delicate dance of forces that allows a star to shine so steadily, a testament to the harmony of cosmic forces. Here's another intriguing detail. The fusion processes in stars are so finely tuned that even slight changes in physical constants could alter the universe profoundly. The precise balance of forces and reactions in fusion ensures that stars produce the right amount of light and heat. This precision hints at the delicate interdependence of physical laws that govern the universe. Did you know that some stars, known as blue stragglers, appear younger than their companions in a stellar cluster? This anomaly is thought to result from a sort of rejuvenation, where a star gains mass from a companion or through collision, reigniting fusion and appearing younger. It's as if these stars have found a way to turn back time, defying their expected life cycle. Speaking of unexpected processes, consider the phenomenon of helium flash. This is a dramatic burst of fusion in some stars, where helium suddenly ignites in the core after building up without fusing for a long time. The resulting release of energy is so rapid and intense that it's called a flash. Imagine the sudden brightness as the star briefly outshines its usual self, a momentary blaze in its long journey. In the grand tapestry of the universe, fusion in stars tells a story of creation and destruction, balance and transformation. Each star, with its unique fusion path, contributes to the ever-evolving cosmos. As you ponder these celestial wonders, may they inspire a sense of awe and excitement about the mysteries that lie beyond our reach. Let your thoughts drift gently among the stars, where fusion weaves the very fabric of the universe. Imagine the vast expanse of the cosmos, where stars twinkle like distant memories of the universe's early days. Did you know that the first stars, called population 3 stars, were composed almost entirely of hydrogen and helium? These primordial stars were the first to ignite nuclear fusion and paved the way for the formation of heavier elements. Their short but intense lives ended in spectacular supernovae, seeding the cosmos with the ingredients for new stars and planets. It's a humbling thought that the universe's early stars laid the foundation for the diverse and complex cosmos we see today. Speaking of cosmic diversity, have you ever heard of Wolf-Rayet stars? These are massive stars known for their fierce winds and high temperatures, capable of stripping away their outer layers. The exposed inner layers undergo intense fusion, resulting in strong emissions of ionized helium and carbon. These stars are like cosmic furnaces, their surfaces ablaze with fusion activity, creating a vivid spectacle in the night sky. And here's a fascinating notion. Some stars are so massive that their cores become incredibly dense, forming neutron stars after a supernova. In these cores, electrons and protons merge to form neutrons, creating a state where fusion is no longer possible. The remnants of these stars are incredibly dense, with a teaspoon of neutron star material weighing as much as a mountain. It's as if the universe has found a way to compress the vastness of a star into a single tiny point. Let me share with you the intriguing case of binary star systems, where two stars are gravitationally bound, orbiting each other in a cosmic dance. In some of these systems, mass transfer from one star to another can reignite fusion, creating a nova. This explosive event is a temporary burst of luminosity, a fleeting yet brilliant reminder of the dynamic nature of stellar fusion. Imagine the surprise of witnessing such a celestial event, a sudden flare of light in the dark canvas of space. Here's something you might find intriguing. White dwarfs, the remnants of stars like our Sun, no longer sustain fusion, yet they continue to cool slowly over billions of years. Eventually, they will become black dwarfs, cold and dark. However, the universe is not old enough yet for any black dwarfs to exist. It's as if these stellar remnants are waiting in quiet anticipation, completing a cosmic cycle over unimaginable timescales. Consider the enigmatic processes within variable stars, which expand and contract in a rhythmic pattern. This pulsation is driven by changes in fusion rates within the star, leading to variations in brightness. The study of these stars, known as asteroseismology, allows astronomers to peer into their interiors, unlocking secrets about their structure and the fusion processes at play. It's like listening to the heartbeat of a star, each pulse a story of fusion happening deep within. Did you know that hypernovae, even more powerful than typical supernovae, occur in some of the universe's most massive stars? These colossal explosions are caused by rapid core collapse, with fusion processes ceasing abruptly as the core succumbs to gravity. The immense energy released can result in the formation of a black hole and the emission of gamma-ray bursts, among the most energetic events in the universe. Imagine the sheer magnitude of such an explosion echoing across the vastness of space. Here's an interesting tidbit. The Sun, our closest star, engages in a delicate fusion process known as the proton-proton chain. This sequence of reactions converts hydrogen into helium, releasing energy that powers the Sun's light and heat. The proton-proton chain is the dominant fusion process in stars like our Sun, a quiet yet relentless engine that has fueled our star for billions of years. It's a gentle reminder of the simplicity and elegance of nature's processes sustaining life on our planet. The fascinating realm of brown dwarfs, often referred to as failed stars, adds another layer to our understanding of stellar fusion. These objects are not massive enough to sustain hydrogen fusion in their cores. Instead, they rely on the fusion of deuterium, a heavy isotope of hydrogen, and other minor fusion processes. Brown dwarfs blur the line between stars and planets, illustrating the diversity of celestial bodies formed through fusion. You might be surprised to learn about the Chandrasekhar limit, a critical threshold in stellar evolution. This is the maximum mass a white dwarf can have before becoming unstable and potentially collapsing into a neutron star or black hole. The limit is approximately 1.4 times the mass of our Sun, illustrating how fusion processes and gravitational forces interplay in determining a star's ultimate fate. Lastly, let's delve into the role of metallicity in star formation and fusion. Metallicity refers to the abundance of elements heavier than hydrogen and helium in a star. High metallicity can influence a star's evolution and fusion processes, affecting characteristics such as temperature and brightness. It's a subtle reminder of how interconnected elements and processes shape the stars we observe and study. With these insights into the mysterious and dynamic processes of nuclear fusion in stars, allow your imagination to wander among the celestial wonders. Each fact is a glimpse into the extraordinary workings of the universe, a testament to the beauty and complexity of the cosmos. As you drift gently towards sleep, may these stellar mysteries fill your dreams with curiosity and wonder. Have you ever wondered how stellar nurseries, the birthplaces of stars, are teeming with potential for nuclear fusion? These vast clouds of gas and dust, known as nebulae, are where stars begin their journey. Within these stellar nurseries, gravity pulls material together, forming dense regions called protostars. As these protostars grow, their cores heat up, eventually reaching the temperatures and pressures necessary for nuclear fusion to ignite. It's like the universe has its own nursery, cradling the beginnings of countless stars. Speaking of beginnings, did you know that the temperature required for fusion in a star's core is incredibly high, around 10 million degrees Celsius? This searing heat is necessary to overcome the electrostatic repulsion between atomic nuclei. Imagine the intense environment required to spark the fusion process, a fiery crucible hidden within the heart of every star. In some stars, fusion goes beyond the simplest elements. Take carbon fusion, for instance, which occurs in more massive stars. When the core temperature climbs to around 500 million degrees Celsius, carbon nuclei can begin to fuse. This process releases even more energy and continues to build heavier elements such as oxygen and neon. It's fascinating to think about how the elements essential to life are forged in the fiery interiors of stars. Fusion does not only happen in the visible spectrum. Stars also emit energy in the form of neutrinos, elusive particles produced during nuclear reactions in their cores. These tiny particles pass through matter almost undetected, traveling vast distances at nearly the speed of light. Neutrinos provide a unique glimpse into the fusion processes occurring deep within stars, silently traversing the cosmos like ghostly messengers of fusion. Have you ever considered that the color of a star can tell us something about the fusion happening within it? Hotter stars tend to be blue, while cooler stars appear red. This color difference is linked to the surface temperature of the star, which in turn is influenced by the rate of fusion occurring in the core. A blue star is often undergoing rapid fusion, emitting more energy and appearing more luminous. It's as if the color of a star is a window into its internal energy production, painting the night sky with a spectrum of stellar activity. Interestingly, not all fusion processes in stars are stable. Some stars experience a phenomenon known as helium flash, a dramatic and rapid burst of helium fusion. This occurs when helium accumulates in the core and suddenly ignites, releasing a vast amount of energy in a short period. It's akin to a cosmic surprise party, where the star suddenly becomes much brighter before settling back into a more stable state. Have you heard about the role of magnetic fields in fusion processes? In certain stars, magnetic fields can influence the movement of charged particles, affecting fusion rates. These fields are twisted and tangled, shaped by the star's rotation and internal movements. They act like invisible hands, guiding and shaping the fusion processes within, a reminder of the complex forces at play in the life of a star. There are also stars known as blue stragglers, which appear younger and hotter than their neighboring stars in old star clusters. These stars are thought to have undergone a rejuvenation of sorts, possibly through the merger of two stars or the accretion of material from a companion. As a result, their fusion processes are reinvigorated, giving them a new lease on life and making them stand out amidst their older peers. Did you know that the fusion processes in stars not only create elements but also influence their distribution across the universe? When stars die, especially in explosive events like supernovae, they scatter the elements forged in their cores into space. These elements then become part of new stars, planets, and even living beings. It's a cosmic cycle of life and death, where fusion not only creates, but also shares the building blocks of the universe. Imagine the scale of fusion in a star cluster, where thousands of stars are born from a single nebula. Each star is a nuclear reactor, contributing to the cluster's overall brightness and energy output. The combined fusion activity of these stars illuminates their surroundings, a collective beacon of fusion-powered light against the vast darkness of space. In some galaxies, intense regions of star formation, known as starburst regions, generate an exceptional amount of energy due to rapid and prolific star formation. Here, nuclear fusion is occurring at an accelerated pace, transforming vast quantities of gas into new stars in a relatively short time. It's as if the galaxy is undergoing a growth spurt, a flurry of fusion activity reshaping its appearance and energy dynamics. It's intriguing to ponder the future of stellar fusion. As stars evolve, their fusion processes change, eventually leading to their transformation into white dwarfs, neutron stars, or black holes. These remnants serve as reminders of the incredible fusion processes that once powered them, leaving behind a legacy of elements and energy that continue to influence the universe. Allow these fascinating insights into the world of nuclear fusion in stars to gently guide you towards a restful slumber. Each fact is a whisper from the cosmos, inviting you to explore the wonders of the universe and its starry secrets. As you close your eyes, let your dreams be filled with the mysteries of fusion and the stars that illuminate our night sky. Did you know that the process of nuclear fusion in stars is so efficient that it converts about 700 million tons of hydrogen into helium every single second in our sun alone? This staggering amount of fusion produces the energy that we feel as sunlight, warming our planet and fostering life. It's remarkable to think of the sheer volume of material being transformed in such a short amount of time, and yet it's just a fraction of the sun's total mass. Here's an intriguing thought. Stars, through their fusion processes, act as cosmic alchemists. They turn lighter elements into heavier ones, a process that takes millions of years. Over a star's lifetime, it gradually changes its core composition, much like how we change and grow over time. It's a constant, slow dance of transformation that shapes the universe. Speaking of transformations, the life cycle of a star is deeply tied to its initial mass. Massive stars, which have more material to burn, go through their fuel more quickly and often end in spectacular supernova explosions. These explosions are so powerful that they briefly outshine entire galaxies. Imagine witnessing such a brilliant display in the night sky, a testament to the immense energy released by nuclear fusion. Can you imagine a star that is so massive it has the potential to collapse into a black hole after its fusion processes have ceased? The gravitational pull in such a star becomes so intense that not even light can escape its grasp. This transformation results in one of the most mysterious objects in the universe, where fusion has played its part and leaves behind a legacy that continues to intrigue scientists. What's fascinating about the universe is how it recycles material through fusion. The elements produced in stars become part of new star systems, planets, and even life forms. Our bodies are made of stardust, the remnants of ancient stars that burned brightly before scattering their elements across the cosmos. It's a humbling reminder of our connection to the universe. In the early universe, only the lightest elements like hydrogen and helium existed. All the heavier elements were formed through fusion processes in stars. It's astonishing to consider that everything you see around you, from the ground beneath your feet to the air you breathe, originated from these stellar forges. Fusion is not just a source of energy, it's the creator of everything we know and see. Did you know some stars can undergo a rare process called the proton-proton chain reaction? This is the dominant fusion mechanism in stars like our Sun. It involves a series of reactions that gradually convert hydrogen into helium, releasing energy that supports the star against gravitational collapse. It's a gentle reminder of the delicate balance maintained within these celestial bodies. Here's a curious fact. Stars are born in stellar nurseries, giant clouds of gas and dust. As these regions collapse under gravity, the material within heats up, eventually reaching the temperatures necessary for nuclear fusion to begin. It's a slow and steady process, like a cosmic gestation period, culminating in the birth of a new star. Imagine a star cluster where stars of different masses are born from the same cloud. Each one has its own path and timeline for fusion, leading to a variety of stellar fates. Some will live fast and die young, while others persist for billions of years. The diversity of stellar life cycles is a beautiful testament to the complexity and variety of the universe. Did you ever wonder how we know so much about nuclear fusion in stars? Astronomers use telescopes to analyze starlight, breaking it down into a spectrum to study the elements present. This technique, known as spectroscopy, allows scientists to understand the fusion processes occurring within stars by examining the light they emit. It's like reading a cosmic signature that reveals a star's inner workings. Consider the fascinating role of binary star systems in fusion processes. In these systems, two stars orbit a common center, influencing each other's evolution. Material can be transferred from one star to another, affecting their fusion and sometimes leading to dramatic events like novae, or even the complete merger of the stars. Such interactions create a dynamic and interconnected stellar dance. In some cases, fusion within a star can result in the expulsion of its outer layers, creating beautiful nebulae. These are often seen as colorful clouds in the sky, remnants of the star's former self enriched with elements forged in its core. This process highlights the cycle of creation and destruction inherent in stellar evolution, painting the cosmos with remnants of past fusion. One of the most amazing things about fusion is its role in regulating a star's life. Fusion provides the outward pressure needed to counteract gravity, keeping the star stable. When fusion stops, the balance is lost, and the star begins to collapse. This delicate equilibrium is essential for a star's longevity and for maintaining the conditions necessary for life on planets like ours. Fusion not only shapes individual stars, but also influences the evolution of entire galaxies. The collective energy from billions of stars can drive galactic winds, affecting the distribution of gas and dust and influencing future star formation. The ripple effects of fusion extend far beyond the stars themselves, impacting the structure and evolution of the universe on a grand scale. As you ponder these cosmic wonders, let the gentle hum of fusion in stars lull you into a peaceful state of rest, inviting you to dream of the vast universe and the countless stars illuminating the night sky. Let's take a deeper journey into the intriguing world of nuclear fusion in stars, where the cosmos holds endless surprises. Have you ever contemplated the immense pressure at a star's core? At the heart of a star, the pressure is so extreme that it exceeds the force of Earth's entire atmosphere over 100 times. This pressure is essential for overcoming the natural repulsion between atomic nuclei, allowing fusion to occur and releasing the energy that powers the star. Did you know the Sun's core temperature is about 15 million degrees Celsius? Such staggering heat is necessary for the intense fusion reactions taking place. Despite this inferno, the Sun's outer layers are much cooler, creating a fascinating temperature gradient that keeps our solar system in balance. Here's something intriguing. Fusion reactions in stars are incredibly efficient. Just a small amount of hydrogen fuel can produce an enormous amount of energy. For instance, the fusion of about 400 kilograms of hydrogen in the Sun produces enough energy to supply the entire world's power needs for a day. It's a testament to the power locked within the smallest atoms. Speaking of energy, did you know stars can adjust their fusion rates? When a star begins to run low on fuel, the rate of fusion slows down, allowing the star to conserve its remaining resources. This self-regulating behavior ensures that a star can maintain equilibrium and resist collapse for as long as possible. In the spectrum of stars, there are some known as red giants. These stars have exhausted the hydrogen in their cores and now fuse helium into heavier elements, like carbon and oxygen. The result is an enormous expansion, turning the star into a swollen, luminous giant. This transformation highlights the dynamic nature of fusion as stars evolve over time. Let's consider the remarkable efficiency of fusion in producing elements. A star like the Sun will convert about 10% of its hydrogen supply into helium over its lifetime. This might seem limited, but the energy released is more than enough to sustain the Sun's brightness and warmth for billions of years, showcasing the profound balance orchestrated by fusion. Did you know that the most massive stars can reach core temperatures exceeding 100 million degrees Celsius? These extreme conditions allow them to fuse heavier elements like silicon and iron, a process impossible in smaller stars. This capability marks a significant difference in fusion processes based on a star's mass and composition. In binary star systems, fusion can lead to surprising phenomena. When one star in such a system evolves into a white dwarf, it can draw material from its companion star. This can trigger a dramatic increase in fusion rates on the white dwarf's surface, resulting in a nova explosion. These spectacular events briefly outshine entire galaxies, demonstrating the explosive potential of fusion. Another captivating aspect of fusion is its role in star formation. In regions of space dense with gas and dust, the gravitational pull brings material together, forming new stars. The onset of fusion within these nascent stars provides the pressure to counterbalance gravity, stopping the collapse and marking the official birth of a star. Have you ever wondered why stars twinkle in the night sky? This effect, known as scintillation, is caused by Earth's atmosphere. However, it's fascinating to think that beneath this shimmering view, nuclear fusion is steadily transforming simple hydrogen into a complex array of elements, a process as stable as it is profound. Interestingly, not all stars shine with the same brightness. A star's luminosity is determined by its size and the rate of fusion occurring in its core. Larger, hotter stars burn fuel rapidly and shine brightly, but have shorter lifespans. In contrast, smaller, cooler stars, like red dwarfs, burn their fuel slowly, making them long-lived and stable contributors to the cosmic dance. Let's explore the idea of stellar nucleosynthesis, where fusion processes within stars produce new elements. This is the primary method by which the elements heavier than hydrogen and helium are created in the universe. Without nucleosynthesis, the variety of elements necessary for forming planets and life would not exist, underscoring the vital role of fusion beyond mere energy production. Are you curious about the end stages of stellar evolution? When a massive star exhausts its nuclear fuel, it may undergo a spectacular supernova explosion, scattering its enriched material into space. This debris becomes the building blocks for new stars and planets, illustrating the cycle of creation and destruction driven by fusion. Finally, consider the role of fusion in the cosmic microwave background radiation, the afterglow of the Big Bang. While not a direct product of stellar fusion, this radiation forms the backdrop against which stars and fusion history unfold, providing a vital clue to the universe's early conditions and the ongoing cycle of stellar creation. As we unravel these intricate details, fusion emerges as a central, unifying force in the cosmos. It is not only a source of energy, but also a creator and sustainer, continually shaping the universe and offering a sense of continuity and wonderment as you drift into a tranquil slumber, pondering the stars and their timeless dance. Did you know that nuclear fusion in stars is responsible for creating almost every element in the universe? It's astonishing to think that the carbon in your body, the oxygen you breathe, and even the iron in your blood were all forged in the heart of stars. This cosmic alchemy is an ongoing process, continually enriching the universe with new materials. Speaking of transformation, here's something fascinating. When massive stars reach the end of their life cycles, these incredibly dense objects, formed after a supernova, can pack the mass of the Sun into a sphere only about 20 kilometers in diameter. Imagine the density and power within such a small space, all due to the remnants of nuclear fusion. Now, let me share another intriguing fact. The temperature and pressure conditions required for fusion are so extreme that they can only occur naturally in stars. On Earth, scientists have been striving to replicate these conditions for clean energy production, but achieving and sustaining fusion has proven to be a monumental challenge. Despite these hurdles, the pursuit continues, driven by the promise of a nearly inexhaustible energy source. Here's something you might not expect. The fusion process in stars is incredibly slow and controlled. In our Sun, it takes about 10 billion years to convert its entire hydrogen supply into helium. This gradual pace ensures a long and stable lifespan, providing the right conditions for life to develop on surrounding planets. Can you imagine the delicate balance required for such a prolonged and steady process? Interestingly, stars can also undergo a fusion process known as helium burning. This occurs after a star has exhausted its hydrogen fuel, and it's fascinating because it leads to the creation of elements like carbon and oxygen, which are crucial for life as we know it. Without this next stage of fusion, the universe would lack many of the elements that form the building blocks of planets and living organisms. Have you ever thought about how fusion influences a star's color? The hotter and more massive the star, the faster it burns its fuel, often resulting in a bluish hue. In contrast, cooler stars burn more slowly and appear red. This color spectrum is not just a beautiful phenomenon to observe in the night sky, but also a telltale sign of the underlying fusion processes at work within the stars. Another surprising aspect is the role of magnetic fields in stars. These fields can influence fusion by shaping the movement and flow of plasma within the star. In some cases, they create sunspots on the star's surface, which are cooler regions resulting from magnetic activity affecting the fusion processes beneath. These intricate interactions add another layer of complexity to the already fascinating dynamics of stellar fusion. Did you know that some stars are capable of undergoing an event called helium flash? This explosive process occurs when a star's core contracts and heats up to the point where helium fusion ignites suddenly. The energy release is so intense that it can temporarily outshine whole regions of a galaxy, a testament to the power of fusion beyond the slow and steady burn we typically associate with stars. Thinking about binary star systems brings to mind an interesting scenario. When stars in such systems are close enough, they can exchange material, a process known as mass transfer. This exchange can alter the fusion processes within each star, sometimes even leading to the birth of exotic stellar objects like blue stragglers, which are stars that appear younger than they are due to renewed fusion activity. Here's a curious fact. The most massive stars, those with mass more than 8 times that of the Sun, can fuse elements up to iron. However, fusion of iron doesn't produce energy. Instead, it requires energy. This marks the beginning of the end for such stars, as they can no longer sustain themselves against gravitational collapse, leading to some of the universe's most dramatic events. Speaking of dramatic events, let us consider gamma-ray bursts, which are among the most energetic phenomena observed in the universe. Some of these bursts are thought to result from the collapse of massive stars after their fusion processes have ceased, releasing immense amounts of energy in a very short time. The power of these bursts is a stark reminder of the energy bound within stellar fusion. Moving on to another captivating idea, the concept of fusion within brown dwarfs. These are objects that straddle the line between massive planets and true stars. Though they cannot sustain hydrogen fusion like stars, they can fuse deuterium, a heavy form of hydrogen, under certain conditions. This limited fusion capability highlights the diverse ways in which nuclear processes occur across different cosmic bodies. Finally, let us ponder on the idea of cosmic recycling. The elements created through fusion in the heart of stars are spread throughout the universe when stars die, particularly during supernova. This material eventually coalesces into new stars, planets, and even living organisms, illustrating a grand cycle of creation and destruction. Fusion, in this light, becomes a fundamental process connecting the birth and evolution of stars to the very emergence of life itself. Contemplating these fascinating facets of nuclear fusion in stars provides a deeper appreciation for the universe's complexity and beauty. It's a reminder of the vast, interconnected systems at play, guiding the cosmos through its endless journey. As you reflect on these wonders, let yourself drift into a peaceful sleep, soothed by the knowledge of the stars and their eternal ballet across the night sky. A fascinating thought to consider is the sheer diversity of stars in the universe and how each variety undergoes fusion in unique ways. For instance, did you know that red dwarfs, the most common type of star, burn their hydrogen fuel so slowly that they can live for trillions of years? This longevity means they have yet to evolve into their later stages, which makes red dwarfs a particularly intriguing subject for astronomers trying to understand stellar evolution. Here's something that might surprise you. The biggest stars, known as hypergiants, live fast and die young. They burn through their nuclear fuel at an astonishing rate, sometimes exhausting their supplies in just a few million years. The rapid fusion processes within these colossal stars lead to spectacular and often violent deaths, typically exploding as supernovae, enriching the surrounding space with heavy elements. Thinking about fusion in stars brings to mind the remarkable fact that different fusion processes can occur simultaneously in a single star. In the later stages of a massive star's life, it can have multiple shells of fusion occurring at different depths, each burning a different element. This layered burning is akin to a cosmic onion, revealing the intricate complexities of stellar life cycles. Speaking of cosmic onions, have you considered the role of neutrinos in stellar fusion? These nearly massless particles are produced in vast quantities during fusion reactions. Because they hardly interact with matter, they escape from the star almost instantly, carrying away energy and providing valuable clues about the processes occurring deep within the stellar core. It's curious to think that the very process of fusion influences the shape and size of a star. For example, stars that rotate rapidly can become oblate, flattening at the poles and bulging at the equator due to centrifugal forces. This shape alteration can affect the fusion rates within the star, demonstrating how dynamic and responsive these celestial bodies are to internal and external forces. Here's an intriguing aspect. Tiny variations in fusion rates can have significant impacts over long timescales. Even a slight increase in the fusion rate in our Sun would lead to a noticeable rise in temperature on Earth, affecting climate and potentially altering the course of evolution. This delicate balance underscores the role of fusion in sustaining conditions for life on planets. Did you know that the fusion of helium into heavier elements releases less energy than hydrogen fusion? This lower energy output means that as stars progress to fusing heavier elements, they often need to compress and heat their cores to maintain equilibrium. This escalating pressure and temperature can lead to dramatic transformations in a star's structure and behavior. Another surprising tidbit is that some stars known as pulsars are remnants of supernova that once housed intense fusion processes. Pulsars are neutron stars, incredibly dense with powerful magnetic fields, and they emit beams of radiation from their poles. As they spin, these beams sweep across space like lighthouse beacons, a mesmerizing reminder of the fusion-fueled cataclysms that birthed them. It's fascinating to ponder how fusion efficiency varies between stars of different masses. Lower mass stars utilize their fuel more efficiently than their massive counterparts, allowing them to have longer lifespans and a more stable existence. This efficiency highlights the diverse strategies stars employ to maintain their internal balance and prolong their luminous lives. Let us consider the phenomena of stellar winds, which are streams of charged particles flowing from a star's surface. These winds are a byproduct of fusion and play a crucial role in shaping the surrounding space environment. For massive stars, stellar winds can be so intense that they significantly strip away the star's outer layers, affecting the longevity and ultimate fate of the star. Here's something that might pique your curiosity. Fusion can lead to the formation of exotic forms of matter. In the intense environments within stars, particles are squeezed together so tightly that they form new states of matter, such as degenerate matter in white dwarfs or strange matter in hypothetical strange stars. These fascinating materials challenge our understanding of physics and the universe. The interplay between fusion and magnetic fields in stars is another captivating subject. In some stars, intense magnetic activity can lead to dramatic flares that release vast amounts of energy into space. These stellar flares are a testament to the energetic potential of fusion as well as the dynamic interplay of forces within a star. Have you ever wondered about the concept of fusion thresholds in stars? Not all stars can ignite fusion equally. There's a minimum mass required for a star to sustain hydrogen fusion, commonly referred to as the stellar mass threshold. Below this threshold, objects like brown dwarfs form, unable to sustain the same continuous fusion that powers true stars. A fascinating detail about fusion is its role in planetary formation. The energy and matter ejected by stars during their life cycles through both stellar winds and supernovae, contribute to the dust and gas clouds that eventually give birth to new stars and planets. This cosmic recycling ensures that fusion not only shapes the stars themselves, but also the worlds that orbit them. In this endless cycle of fusion and reformation, the universe continually creates new possibilities for life and structure, guided by the silent yet powerful processes of fusion burning brightly in the hearts of stars. As you lay back and imagine the vastness of space, let these thoughts of cosmic processes and stellar wonders lull you into a state of restful contemplation. Imagine the vast tapestry of the cosmos, where each star is a tiny point of light, yet within each one, nuclear fusion is the powerful engine driving its brilliance. It's astonishing to realize how each stage of fusion creates distinct elements crucial for the cosmos. Stars act as stellar forges, creating elements from helium up to iron in their cores. This element creation is not just a byproduct, but a defining feature of stellar evolution, enriching the universe with the building blocks of planets, moons, and life itself. As we ponder the life cycle of stars, have you considered the extraordinary fate of those that reach the end of their fusion-fueled lives? When a massive star exhausts its nuclear fuel and can no longer support itself against gravitational collapse, it might form a black hole, a region in space where gravity is so strong that nothing, not even light, can escape. This transformation from a brilliant star to a mysterious black hole is a dramatic testament to the immense power of nuclear fusion and its eventual limits. Speaking of limits, did you know that there is a theoretical maximum to the size a star can reach? Known as the Eddington limit, it is the balance point where the outward pressure from radiation equals the gravitational pull inward. Beyond this limit, a star's intense light can push its outer layers away, essentially preventing the star from growing any larger. This limit highlights the finely tuned physics governing stellar formation and growth, all influenced by the ongoing fusion within. While stars are the main stage for nuclear fusion, have you ever wondered what happens when stars collide? In rare cosmic dances, when two stars merge, the resulting burst of fusion can briefly outshine entire galaxies. These events, known as kilonovae, are explosive displays that produce heavy elements like gold and platinum. It's remarkable to think that such precious materials on Earth owe their existence to these dramatic stellar encounters. Here's something intriguing. The Sun, our closest star, is powered by a specific type of fusion known as the proton-proton chain reaction. While this process is efficient for stars like the Sun, more massive stars predominantly use another pathway called the CNO cycle, which involves carbon, nitrogen, and oxygen as catalysts for hydrogen fusion. The existence of different fusion pathways showcases the adaptability and complexity of stellar processes, each tailored to the unique conditions of the star. Considering the diversity of stars, have you ever thought about the role of metallicity in stellar fusion? Metallicity refers to the presence of elements heavier than hydrogen and helium in a star. It's fascinating to realize that stars with higher metallicity can have different fusion processes and life cycles compared to those with lower metallicity. These variations affect everything from the star's color to its lifespan and ultimate fate, illustrating the intricate interplay between composition and fusion. Now, let's explore the concept of stellar nucleosynthesis, where fusion not only creates elements, but also releases neutrons into the star's environment. These neutrons can be captured by other nuclei, leading to the creation of even heavier elements beyond iron. This process, known as the S process, is a slower fusion reaction that gradually builds up heavy elements over time, contributing to the rich diversity of materials found in the universe. In the grand scheme of things, isn't it captivating to think about the role of fusion in star clusters? Within these dense collections of stars, close proximity allows for gravitational interactions that can influence individual stars' fusion rates and life cycles. In some cases, stars can exchange mass or even merge, altering their evolutionary paths. This dynamic environment demonstrates how fusion is not just an isolated process within single stars, but a communal phenomenon influenced by the stellar neighborhood. Have you ever marveled at the way astronomers can learn about stellar fusion from light? The spectra of stars, or the light they emit, carry signatures of the elements being fused in their cores. By studying these spectra, scientists can unravel the fusion processes occurring within, providing insights into the star's age, composition, and future. This method of stellar archaeology opens up a window into the hidden workings of nuclear fusion across the cosmos. Lastly, consider the intriguing concept of stellar equilibrium. Stars are constantly balancing the forces of gravity pulling inward and pressure from fusion pushing outward. This equilibrium is delicate, and any change in fusion rates can lead to expansion or contraction of the star. It's a dynamic dance that ensures stability, allowing stars to shine steadily for billions of years. This stability is vital for life on planets like Earth, where the consistent energy output of the Sun supports climates and ecosystems. As you reflect on these surprising facets of nuclear fusion in stars, let the knowledge of cosmic creation and destruction cradle you into a peaceful state, where the mysteries of the universe become gentle whispers of wonder in the night. Let me share with you the incredible fact that the energy produced by nuclear fusion in stars is so immense that it powers entire galaxies, lighting up the universe with its brilliance. This energy is a result of tiny subatomic particles colliding at unimaginable speeds, igniting the stars we see twinkling in the night sky. Can you imagine the sheer magnitude of this power emanating from something as distant as a star? As we delve deeper, consider this. The process of nuclear fusion in stars is not only responsible for energy, but also for creating magnetic fields. These fields can twist and tangle, sometimes releasing energy in the form of solar flares or coronal mass ejections. Such phenomena can have dramatic effects even here on Earth, influencing everything from satellite operations to auroras that paint our skies with vibrant colors. It's fascinating how the distant dance of fusion can have ripples that reach us on our tiny blue planet. Did you know that not all stars have the same fusion efficiency? Smaller stars, like red dwarfs, burn their fuel much more slowly and can last for tens of billions of years. In contrast, massive stars have a voracious appetite for fuel, burning through their reserves in just a few million years. This disparity in lifespan is a reminder of how diverse and varied the cosmos can be, with each star following its unique path dictated by the fusion within. Here's another fascinating aspect. While we often think of stars as perfect spheres, the immense energy from nuclear fusion can actually cause some stars to flatten slightly at their poles. This oblate shape results from the rapid rotation of the star, combined with the outward pressure of fusion. It's a subtle yet significant effect, providing clues about the internal dynamics and rotation rates of these distant celestial bodies. Speaking of rotation, have you ever considered how fusion impacts a star's spin? As stars age and their fusion processes evolve, they can lose angular momentum, causing their rotation to change. This loss of spin can affect everything from the star's magnetic field to its overall stability. It's amazing to think that the silent internal workings of fusion can influence such macroscopic properties. And here's something truly mind-boggling. The energy generated by fusion in the sun takes thousands of years to reach the surface. Photons produced in the core are constantly absorbed and re-emitted by particles in the sun's outer layers, a process called radiative diffusion. This slow journey underscores the vastness and complexity of stellar interiors, where light itself must navigate myriad obstacles before finally escaping into the universe. Have you ever wondered about the role of pressure in stellar fusion? Deep within stars, the intense pressure from gravity is crucial for sustaining fusion reactions. This pressure ensures that atoms are sufficiently close to collide and fuse. However, if a star's core pressure drops, the fusion process can falter, leading to dramatic changes in the star's structure and behavior. It's a delicate balance maintained over billions of years that allows stars to shine steadily. Let us ponder the intriguing behavior of fusion in binary star systems. In these stellar pairs, one star can transfer mass to its companion, effectively fueling its fusion processes. This mass exchange can lead to unexpected changes in the star's life cycles, sometimes triggering explosive events like novae or even supernovae. The interplay between fusion and mass transfer in such systems adds a layer of complexity to our understanding of stellar evolution. Did you realize that fusion in stars also influences their acoustic properties? The sound waves generated by fusion-related movements within a star can travel through its interior, creating oscillations detectable from Earth. By studying these oscillations, astronomers can glean information about the star's internal structure, much like seismologists use earthquakes to study the Earth's interior. It's an incredible blend of sound and science, revealing the hidden symphonies playing out within the stars. And here's a thought-provoking detail. The byproducts of fusion can alter a star's opacity. As fusion progresses, the transformation of hydrogen into helium changes the star's light absorption properties, affecting how energy moves through its layers. This shift in opacity can influence the star's brightness and temperature, gradually altering its appearance and characteristics over time. Have you ever imagined that fusion could play a role in planetary formation? The heavy elements forged in the hearts of stars are scattered into space when these stars die, providing the raw materials for planets and other celestial bodies. Without the ongoing march of fusion across generations of stars, the building blocks of planets, and indeed life itself, would be absent from the universe. Finally, contemplate the concept of fusion as a timekeeper in the universe. The rate at which fusion occurs can help determine the age of stars, offering insights into the timeline of cosmic events. By understanding fusion processes, astronomers can piece together the story of the universe, tracing its history from the Big Bang to the present day. As you let these celestial musings embark on a gentle journey through your thoughts, allow the quiet grandeur of nuclear fusion to inspire a sense of tranquility and wonder. Each star, through its fusion-fueled existence, contributes to the intricate tapestry of the cosmos, a symphony of creation and transformation that echoes softly in the vastness of space. Let me share with you the curious phenomenon of stellar nurseries. These are regions in space where clouds of dust and gas, called nebulae, gather and eventually give birth to stars through the process of fusion. Within these nurseries, gravity pulls particles together, heating them until they reach the temperatures needed for nuclear fusion. It's amazing to think of these cosmic cradles nurturing new stars, each destined to light up the universe in its own unique way. Speaking of beginnings, have you ever wondered how stars ignite their fusion processes initially? The answer lies in the critical mass. A protostar must accrue enough mass to generate the immense pressure and temperature required for fusion to commence. Without reaching this threshold, gravity alone isn't sufficient to spark the nuclear fire within. It's a delicate cosmic dance where mass, temperature, and pressure come together to light the celestial flames. Here's a fascinating tidbit about the diversity of fusion reactions. While our Sun primarily fuses hydrogen into helium through the proton-proton chain, more massive stars employ a different mechanism known as the CNO cycle, which involves carbon, nitrogen, and oxygen as catalysts. This variation highlights the adaptability of fusion processes based on a star's mass and composition, painting a picture of diversity even among seemingly similar stars. Did you know that the fusion occurring within stars has a direct connection to the elements found in your body? Every atom of carbon, calcium, and iron in your makeup was once forged in the heart of a star. It's poetic to think that stars are the cosmic forgers of the elements, and in some profound way, we carry their ancient light within us. And then there's the enigma of stellar winds. These are streams of charged particles perpetually flowing outward from a star, driven by energy from its fusion processes. Over time, stellar winds can strip away a star's outer layers, especially in massive stars nearing the end of their life. This shedding of material enriches the surrounding interstellar medium, seeding it with elements necessary for future star formation. Let's consider for a moment the impressive resilience of red dwarf stars. These small, cool stars are incredibly efficient at sustaining fusion, consuming their hydrogen fuel at a slow and steady pace. This efficiency grants them lifespans that can extend beyond 1 trillion years, far exceeding the current age of the universe. It's a testament to the enduring nature of fusion, quietly sustaining these stars through the ages. Have you ever imagined the cosmic ballet of binary star systems? In some cases, stars in these systems engage in what's known as a common envelope phase, where one star's outer layers engulf its companion. This dramatic interaction can alter the evolution of both stars, influencing their fusion processes and sometimes leading to exotic end states like binary white dwarfs or neutron stars. Here's something intriguing: the presence of stellar oscillations or starquakes. Much like earthquakes on our planet, these oscillations are caused by changes in a star's internal structure, possibly due to shifts in its fusion processes. By studying the frequency and pattern of these starquakes, astronomers can gain insights into the star's composition and the fusion reactions occurring within. Consider the role of neutrinos, elusive particles produced in vast quantities during fusion. These particles pass through matter almost without interaction, making them incredibly challenging to detect. However, by capturing these ghostly messengers from the Sun, scientists can probe the ongoing fusion reactions and validate theoretical models of stellar behavior. Did you realize that fusion efficiency can affect a star's ultimate fate? In stars less than 8 times the mass of the Sun, fusion ceases with the formation of a carbon-oxygen core, leading them to eventually shed their outer layers and form white dwarfs. More massive stars, however, continue fusing heavier elements until they reach iron, at which point fusion no longer yields energy, leading to collapse and often resulting in a supernova explosion. Let's delve into the mesmerizing phenomenon of pulsars. These are neutron stars, remnants of supernova explosions that rotate rapidly and emit beams of radiation. The fusion processes that preceded the supernova laid the groundwork for the dense, rapidly spinning neutron star that remains. It's a stellar coda, a complex fusion song that continues to echo across the universe. And here's an intriguing question. What about the temperature extremes within stars? At the core of a star, where fusion occurs, temperatures can soar to 15 million degrees Celsius, while the surface may be relatively cool at just a few thousand degrees. This dramatic gradient is a testament to the powerful forces at play within, sculpting stars from their fiery centers to their cooler exteriors. Did you know that stellar fusion is a key driver of cosmic recycling? The matter ejected from dying stars through supernovae and stellar winds eventually coalesces into new stars and planets. This cycle of birth, death, and rebirth underscores the interconnectedness of the cosmos, a perpetual flow of material reshaped by fusion's powerful hands. Finally, ponder the notion of fusion as a cosmic clock winding down. As stars exhaust their nuclear fuel, their fusion rates change, altering their size, temperature, and brightness. These changes serve as timekeepers, marking the passages of stellar life and providing us with a means to understand the chronological tapestry woven by the stars. The dance of fusion, in its myriad forms, is a gentle reminder of the universe's enduring, ever-unfolding narrative. Can you imagine a universe where stars didn't rely on nuclear fusion to shine? Without this process, the night sky would be devoid of the twinkling stars we so often gaze upon. It's fascinating to think that fusion is not only the source of a star's luminosity, but also a vital ingredient in the cosmic recipe for life. Speaking of which, did you know that the fusion process in stars can create antimatter? Yes, in certain reactions, such as those involving high-energy photons, particles of antimatter are produced. Though they quickly annihilate, their fleeting existence is a reminder of the complex, dynamic nature of stellar cores. Here's an intriguing connection: the concept of stellar nucleosynthesis, which explains how fusion reactions in stars create elements heavier than hydrogen and helium. This process is responsible for the diversity of elements we find today, from the calcium in our bones to the gold in our jewelry. Isn't it remarkable to think that the universe's alchemy happens right within the stars? And considering this cosmic alchemy, did you realize that not all stars end their lives in the same way? Some stars, as they exhaust their fusion capacity, form peculiar remnants known as magnetars. These are a type of neutron star with incredibly strong magnetic fields, which can be trillions of times more powerful than Earth's. Here's something thought-provoking. The influence of fusion goes beyond the visible spectrum. Stars emit vast amounts of energy in the form of X-rays and ultraviolet radiation, which play a crucial role in shaping the atmospheres of planets. This radiation can drive atmospheric chemistry, influencing habitability, and even sparking the chemical reactions necessary for life as we understand it. Have you ever wondered about the role of fusion in determining a star's color? A star's temperature, dictated by fusion activity, directly affects the color of light it emits. Cooler stars shine in red or orange hues, while hotter stars appear blue or white. This color spectrum serves as a visual cue, helping astronomers classify stars and understand their fusion dynamics. And speaking of dynamics, consider the phenomenon of quasi-periodic oscillations. These are fluctuations in brightness observed in certain stars and binary systems. They provide clues about the inner workings of stars, hinting at the intricate ballet of matter and energy within. Isn't it amazing how even small variations can reveal so much about the hidden processes of fusion? Here's another captivating insight. In some regions of the universe, intense gravitational forces can cause fusion to occur in unexpected places. For example, in the dense environments of galactic centers, gas clouds can undergo fusion, creating stars in a region otherwise hostile to star formation. It's a testament to the resilience of fusion, finding a way even in the most challenging conditions. Have you ever considered the sheer scale of energy released by nuclear fusion in stars? The energy produced by our Sun every second is equivalent to the detonation of billions of nuclear bombs. Despite this immense power, the Sun remains stable, its fusion reactions precisely balanced by the outward pressure of radiation and the inward pull of gravity. This delicate equilibrium allows the Sun and other stars to shine steadily over billions of years. Speaking of balance, did you know that some stars can experience a phenomenon called helium flash? This occurs in stars with low mass when helium fusion ignites suddenly, leading to a dramatic increase in energy output. This brief but intense phase can alter the star's structure and evolution, showcasing the unpredictable nature of stellar life cycles. As we explore further, consider the role of fusion in the cosmic web that connects galaxies. The energy and elements released by stars during their lifetimes contribute to the formation of new stars and galaxies, weaving a complex tapestry that spans the universe. This interconnectedness is a reminder of the universal bonds formed by fusion, linking distant corners of the cosmos in a grand, ever-expanding narrative. Here's a comforting thought. Despite the violent and explosive events associated with fusion, such as supernovae, these occurrences are rare on the cosmic timescale. Most stars spend the vast majority of their lives quietly fusing hydrogen into helium, providing the stability necessary for life to emerge and evolve. Did you realize that fusion in stars can influence the potential for life on planets orbiting them? The stability and longevity of a star's fusion process determine the habitable zone, the region where conditions might allow liquid water to exist. This zone shifts and changes as a star evolves, highlighting the dynamic interplay between stellar fusion and planetary environments. Speaking of environments, have you ever heard of the phenomenon called stellar convection? This process involves the movement of plasma within a star, transporting energy from the core to the surface. Convection plays a crucial role in the fusion cycle, helping distribute energy evenly and preventing catastrophic imbalances. As we draw these reflections together, consider how fusion is a common thread that binds us to the stars. It's a force of creation and destruction, a process both ancient and ever-renewing, shaping the universe and everything within it. So next time you gaze at the night sky, remember that the light you see is a product of fusion's timeless dance, a reminder of the profound connections between us and the cosmos. As we drift into dreams, let these celestial stories fill our imaginations, guiding us through the mysteries of the universe and the wonders within each star. Let me share a rather intriguing aspect of nuclear fusion in stars that you might not have considered. Did you know that fusion in stars is responsible for the creation of the most fundamental cosmic building blocks, like carbon and oxygen? These elements, essential to life, are formed in the hearts of stars through processes like the triple alpha process, where helium nuclei combine to create carbon. It's mind-boggling to think that the air we breathe and the life we cherish owe their existence to the ancient stars that once burned brightly in the cosmos. Speaking of cosmic wonders, here's a surprising fact. Not all fusion reactions are the same. In massive stars, beyond the fusion of hydrogen and helium, a process known as the CNO cycle, involving carbon, nitrogen, and oxygen as catalysts, dominates the energy production. This cycle is less efficient than the proton-proton chain seen in our Sun, but it becomes significant in stars much larger than our own. It's fascinating how different types of fusion reactions can shape the life cycles of stars in various ways. Now, imagine this. In the final stages of a massive star's life, once it can no longer sustain fusion, it undergoes a spectacular transformation. The core collapses under gravity, and in a fraction of a second, a supernova explosion occurs, the brightness of which can outshine an entire galaxy. This cataclysmic event not only marks the death of a star, but also seeds the universe with heavy elements, enabling the birth of new stars and planets. It's astonishing how destruction paves the way for creation in the universe's cycle of life. Have you ever heard about blue stragglers? These are curious stars that seem younger and hotter than their neighbors in star clusters, defying the expected evolution patterns. Scientists suspect that these stars may have gained extra mass through interactions or mergers with other stars, reigniting fusion processes and giving them a youthful appearance. It's a stellar mystery that continues to captivate astronomers, highlighting the complex dynamics of star clusters. Here's something that might surprise you. White dwarfs, the remnants of low to intermediate mass stars, can sometimes reignite in a spectacular fashion known as a nova. When a white dwarf in a binary system accretes enough material from its companion star, the accumulated hydrogen on its surface can undergo runaway fusion, creating a brilliant burst of light. These novas can repeat at intervals, showcasing the ongoing dance of fusion even in the remnants of stars. And did you ever wonder how fusion in stars can influence their size? In a phenomenon called stellar pulsation, some stars expand and contract rhythmically due to imbalances in their fusion reactions. This pulsation can lead to dramatic brightness variations, as seen in Cepheid variables. These stars play a crucial role in astronomical measurements, acting as cosmic lighthouses to help determine distances across the universe. Speaking of variable stars, let's delve into the enigma of throbbing stars. These stars, known scientifically as RR Lyrae variables, exhibit periodic changes in brightness due to pulsations caused by fusion processes. The consistent nature of their pulsations makes them valuable tools for measuring cosmic distances, acting as celestial yardsticks in the vast expanse of the universe. Here's an extraordinary thought. The fusion processes in stars are not just confined to the visible universe. Neutrinos, nearly massless particles produced during fusion reactions, pass through the universe almost undisturbed, including our own bodies. These elusive particles provide crucial insights into the inner workings of stars, acting as cosmic messengers that bridge the gap between the stars and Earth. Did you know that in the late stages of massive stars, a fusion process known as silicon burning occurs? In this process, silicon nuclei fuse to form iron, marking the final fusion stage before the star's core collapses. Iron's formation is significant because it is the heaviest element that can be produced through fusion in stars. Beyond iron, energy must be consumed rather than released, leading to the eventual collapse of the star and the dramatic onset of a supernova. It's fascinating how the life cycle of a star can be dictated by such elemental boundaries. As we ponder these cosmic wonders, consider the phenomenon of spontaneous fusion. In extremely dense and hot environments, like those found in the early universe or in the hearts of supermassive stars, fusion can occur almost spontaneously due to high pressures and temperatures. This rapid fusion process is believed to have played a crucial role in the formation of the first elements shortly after the Big Bang, setting the stage for the universe we see today. And here's a captivating insight. Stars in close proximity can engage in a cosmic dance that affects their fusion processes. In binary star systems, the interaction and exchange of mass between stars can lead to unexpected fusion behaviors. This exchange can result in one star rejuvenating the other, altering their life cycles in unpredictable ways and showcasing the dynamic interplay of forces at work in the universe. As we reflect on these startling revelations about nuclear fusion in stars, it becomes clear that the universe is a vast, interconnected tapestry of cosmic processes. Fusion is not just a force of creation, but also a catalyst for change, driving the evolution of stars and the galaxies they inhabit. The stars, with their enduring fusion fires, continue to inspire awe and wonder, reminding us of the profound connections that link us to the cosmos. As you drift into a peaceful slumber, let these stellar stories nurture your dreams, filling them with the light and mystery of the universe. Let me share something intriguing with you. Even though the fusion process predominantly involves hydrogen, did you know that stars can also fuse helium into carbon and oxygen in what is known as the triple alpha process? This occurs in the cores of red giant stars when temperatures soar to extraordinary levels. It's quite fascinating to think that the carbon in your DNA and the oxygen you breathe were once forged in the hearts of ancient stars. Speaking of which, did you ever wonder how the size of a star affects its lifespan and fusion processes? Larger stars burn through their fuel at a much faster rate, leading to a shorter lifespan. In contrast, smaller stars, like red dwarfs, fuse their hydrogen so slowly that they can live for tens of billions of years, far outliving their larger counterparts. Here's an exciting thought. In the dense environment of a star's core, the intense pressure and temperature allow for fusion reactions that would be impossible on Earth. This is because the star's immense gravitational force compresses its core to the point where nuclei can overcome their natural repulsion and merge. Now imagine this. The fusion process doesn't just produce energy and light, it also propels powerful stellar winds. These winds, composed of charged particles, are crucial for dispersing a star's outer layers and enriching the surrounding space with elements necessary for the formation of new stars. Did you know that the end stages of a star's life are marked by a type of fusion known as neutron capture? This process occurs in supernovae and in the interiors of neutron stars, where rapid or slow neutron captures can form elements heavier than iron, such as gold and uranium. It's astounding to consider that the gold in your jewelry was once forged in the cataclysmic heart of a dying star. Speaking of star endings, have you heard about the phenomenon of pair instability supernova? It occurs in the most massive stars, where the intense radiation pressure in their cores leads to the creation of particle-antiparticle pairs. This process destabilizes the star, resulting in a supernova that completely obliterates it, leaving no remnant behind. Here's something to marvel at. In binary star systems, when a white dwarf and a companion star are in close proximity, the fusion process can lead to the creation of incredibly luminous events known as Type 1a supernovae. These explosions are so bright they can outshine entire galaxies, serving as standard candles to measure astronomical distances. And speaking of measuring distances, did you know that the precise pulsations observed in Cepheid variables, a type of variable star, were pivotal in determining that the universe is expanding? These stars have played a crucial role in shaping our understanding of the cosmos. It's mesmerizing to think that the fusion processes in stars are not uniform. They can create unique phenomena like stellar flares. Stars such as red dwarfs are known for their intense and unpredictable flares, which are powerful bursts of energy caused by sudden changes in the star's magnetic field. These flares can significantly affect the atmospheres of surrounding planets, showcasing the dynamic relationship between stars and their celestial companions. Here's a little-known fact. Some stars experience helium flash events during their red giant phase. This is when helium fusion ignites explosively in the core, releasing an enormous amount of energy in a matter of seconds. Despite its dramatic nature, this event happens deep within the star, invisible to the outside universe but causing significant changes in the star's structure. You might find it fascinating that the study of nuclear fusion in stars has inspired scientists on Earth to replicate these processes in a controlled manner. Projects like tokamaks and stellarators aim to harness fusion power, offering the promise of a clean and virtually limitless energy source. These endeavors remind us of our intrinsic connection to the stars and our ongoing quest to unlock their secrets. And here's a delightful tidbit. The fusion processes in stars are responsible for creating most of the elements found in our periodic table. From the calcium in your bones to the iron in your blood, we are truly made of star stuff, as the late Carl Sagan famously said. This cosmic recycling connects us to the universe in the most profound way, tying our existence to the ancient processes that have shaped stars for billions of years. As you ponder these stellar mysteries, consider this. The ongoing fusion processes in stars not only sustain their luminosity and heat, but also drive the chemical evolution of galaxies. With each generation of stars, new elements are forged and spread throughout the cosmos, enriching interstellar clouds and influencing the formation of future stars and planets. This endless cycle of creation and destruction forms the heartbeat of the universe. Let these thoughts of cosmic processes and the profound beauty of nuclear fusion in stars guide you gently into dreams filled with light and wonder. As you drift off, remember that the stars above are more than celestial bodies. They are storytellers of the universe, weaving tales of creation, destruction, and rebirth. In their glowing presence may you find peace and inspiration, knowing that we are all part of this grand cosmic tapestry.